The video you're about to see is the concluding lecture for this academic year, presented by the Rockland Astronomy Club at Rockland Community College. It was a fantastic lecture on gravitational lensing by Dr. James Hung Soo Chan. Yeah, just go to rocklandastronomyclub.com and you can get all the details about this. Anyway, enjoy this lecture. It's extremely educational and entertaining.
Everybody, and welcome to Rockland Astronomy Club's final lecture series for 2026 spring semester. We want to welcome everybody here, and we are pleased to have with us a very renowned astrophysicist, Dr. James Chang, who is affiliated with the City University of New York and with the American Museum of Natural History. His talk tonight is Gravity Telescopes Bending Light to Reveal the Universe to Us All. So please give a warm welcome to Dr. James Chang.
Okay, so thanks for coming. It's really my pleasure to be here. So I'm James Chan. So today we are going to see some very beautiful pictures. The first one, but we are going to see more. Yeah. So I want to ask here, who is interested in astronomy? Who come here just want to kill some time? I want to kill some time. I want to have some fun. That's my goal. So we will have some fun during this talk. So of course, I hope. First question: how are you today?
Good.
So far, so good. I tell you how I feel today. This picture shows how I feel today. This is a real picture. It's not like an AI Photoshop. No, this is real, coming from the universe. It looks like a Cheshire cat, like Alice in Wonderland. So you can see this smiley face. So this is we say the gravitational lens system. Yeah, you can see the image is a little bit weird, right? Let's go back to this picture. So this picture is coming from, I think, currently the best telescope in the world. I think we got this picture probably four years ago. It's a picture, first image from the James Webb Space Telescope. Anyone heard about it?
Oh, yes.
Yeah, this is probably the currently most expensive telescope human being built. So look at this picture, you see a lot of details. This is a picture from James Webb. And I'm going to show you the image from Hubble telescope. Hubble is also amazing, right? But compared to James Webb, you will see James, not me, James Webb, he shows a lot of details of the universe. Especially this kind of reddish stuff. Because James Webb telescope can see further of the universe. Yeah, that's what I want to show you, how powerful it is. And this telescope will reveal a lot of this kind of beautiful system for us scientists to analyze the data, to understand the universe, and also entertain everyone here. Yeah, because we want to see beautiful pictures. Yeah. How does this effect happen? So now we are going to talk about gravitational lensing. Okay. This is a sheet of the space-time. So if you have the light, if the sheet is flat, which means the space-time is flat, then the light, the traveling path will be straight line, right? It's a flat. But if there's a massive object bend the space-time, now you can see the sheet kind of like a curve. So when the light travels through this kind of the space-time, what would happen? will be bent. Okay? So this is a very basic lensing theory. So the gravity can bend the light. It's coming from the Einstein proposed this idea. Yeah. So this idea is proposed by Einstein, general relativity. Say, okay, so light in fact can be bent by the gravity. But we need the evidence. So there's a guy, Arthur Eddington. He wants to prove this idea is real or not. How does he do? So he observed the position of the stars on the sky. And then, we have the sun, right? So the star from somewhere coming to us, if there's a sun in front or between the star, the furthest star, the source star, and us, the traveling path will be bent by the sun, if Einstein is correct, right? Because the traveling path, if there's a sun in the center, the gravity will bend the light. Okay, so we should be able to see the position is kind of distorted. But if there's a sun, how can you see the stars? It's too bright. It's basically not possible. So he need to wait. Some miracle happen. When the sun is blocked by something else. By what? By the moon. So when the moon block the sunlight, which is when solar eclipse happens, then you can observe the star behind the sun. So that's how he did. So he waited until this day, May 29, 1919. So there's a solar eclipse happen. And he sent 2 ships. One to the Brazil, one to the island, I think it's called Principe. And then set up a telescope, start to observe, waiting for the solar system happen. So when the moon blocked the sunlight, they took the picture. So we're going to see the picture they took. Are you ready? This is the picture. So this is a solar eclipse happened in 1919. So you can see here is the moon, and you can see the kind of corona. And I highlight the position of stars. For you, when you see the picture, okay, I see the picture of star, but how do we know? The light is bent. So the astronomers need to compare the star position and with the sun and without the sun. And they see a little bit tiny shift. Okay? And that's how Einstein general relativity is proved to be right. That's how it happened. So they observe there's a star position, there's an actual position, but the light is bent by the sun. So this is what we really observe. Okay, but it's really tiny. It's really tiny. Yeah. So to get this picture, I think it's kind of incredible. Now, of course, the result when you publish is like in November on the New York Times. So the light all askew in the heavens. Yeah. So Einstein is proved to be right. Yeah. Okay. So when 1919, Einstein had this idea, he derived all the, light will be bent by the gravity, but this is still not lensing yet. Because the whole lensing theory, like how we still get the information or the model of the image I show you, the equation need to wait until like 1936, like 20 years. Yeah, so Einstein, sit down, he said, I want to derive how the model, so he write a little paper, which is on the science. So he derived how lensing effect would be, based on general relativity, how the image would be distorted, he derived that. But this paper is quite interesting, because in the end, he what he wrote is here. So therefore, there's no great chance of observing this phenomenon. It's not possible to observe. Even though I derive for you guys, we cannot see it. It's not possible because the separation is too tiny. You basically cannot see it. Yeah, so it's no way. So he doesn't believe we can see it. 1936. Okay, but at that time, I think human beings still think everything on the sky, they are like stars. Or something called nebula. We don't really know what is that. Okay. So this is the moment human beings start to understand what is galaxy. Okay, so now for us, we know what is galaxy. We know Milky Way is galaxy, and it's just one of the galaxy. But you know what? At that time, we still not really sure. Some people still believe Milky Way is the whole universe. Okay, so that's why I think 1920 something, there's a great debate. Okay, but now we know, of course, Milky Way is one of the galaxies. And by the way, do you know what is the word galaxy coming from?
Milk.
Coming from the milk. So because the gala in Greek is milk. So if you go to Greece, you say gala, they will give you milk. Yeah, so galaxy basically is Milky Way. Yeah. So at that time, we still don't really understand, is there any like a heavy object in the sky? Of course it is. So there's a guy, he wrote a paper, say, on the masses of the nebula and of cluster of nebulae. Okay? So nebulae here, at that time, we know nebula is just kind of blur stuff. Okay? Because at that time, the telescope is still not good enough. Everything blur, we call nebula. Okay, but nebula is nebula. It's coming from, nowadays we know it's coming from the gas. You know there's Orion Nebula. The image is different from the galaxies. Right? Galaxies is a bunch of stars together. But at that time, when people see the image, it just blurs something. Yeah. So this is a moment people start to understand what galaxy is. So Einstein, he think, okay, star cannot really create a lensing image. But galaxies, very, very massive object, is possible. That's why this guy, he wrote this paper. In fact, in the universe, we have a lot of these kind of galaxies and galaxy clusters. They are very, very massive, so you can observe it. So this is a guy, Zwicky. He looked like this, the Swiss astronomer. So he said, no problem, okay. So I said, okay. The first Zwicky, this guy is also quite interesting because he's the one who proposed dark matter. Okay, so he's the first one who thinks dark matter exists. Yeah. So we have a little bit of history. So now we know lensing effect is derived by Einstein, but in fact, long time ago, 1700 years ago, in fact, Newton already has written something. He suggests light could be bent under gravity. He already writes something in his book. So Einstein, yeah, he's really, really smart, but he's not the only one. Newton is the only one, the first one. And then after 100 years, this guy, Johann Georg von Soldner, he first calculate how lensing effect would happen under the Newton gravity. Okay? Because at this time, Einstein still, we don't know where he is. He's in mother's belly, maybe, not even. Yeah. So, this guy, what he can do is he took Newton's theory and he derived the lensing equation, blah, blah, blah. Of course, this is not fully correct, but he's the first one who derived the lensing, derived the distortion of the light under Newton gravity. So, after another 100 years, Einstein first correct the prediction of light deflection. Okay? So, He is the first one who get the equation right. But this idea, in fact, is already happened 200 years. So human being needed 200 years to really get the right answer. It takes so long. Okay? But this one, he derived the light distortion. It's not whole lensing theory yet. And after 4 years, we need to wait for the solar eclipse to get the image to prove this is right. So this first observation evidence. And then 1936, I show you the paper. Einstein first have the full description of general gravitational lensing. So this, you see, we wait for so long to get the whole theory. Yeah, of 200 years. But it's just an idea, lensing can happen. We still don't have the evidence yet. We know light can be distorted, but we want to see the image. We need to wait. 1979. First time we discover a gravitational lens. Okay? You see, we wait for almost 300 years. It's a really, really long time. So, are you ready? We are going to see the first image of gravitational lens. You look like this. This is the first image. Really the first one. We took the picture and it's here. Doesn't look like a lens. Doesn't look like a lens. Like the first image I show you, you can see the arc, beautiful arc. Of course, it's a lens system. But this one, how can we know this is a lens? And I want to give you the feeling how big of this object. Do you have the feeling of how big of the moon is, right? When you look at the sky, you see the moon, you can see the moon by your eyes. So the size of moon is around like 0.5 degree. Okay, 0.5 degree, like angular size. Roughly around your thumbnail, if you look at this. Yeah. And this object, compared to the moon, is like this. Okay, so the moon, imagine if you put out your thumb, this is roughly like the moon, and this is the size of the lens. So this is really, really, really tiny. You need a very good telescope to resolve this. But now we have a pretty good telescope. Okay, now we are going to advance this. This is another image from the ground-based telescope. It's a Sloan observatory, Sloan telescope, like 2.5 meter. And from this image, you already can somehow see these two little bright objects close to each other. And now we are going to see the image coming from Hubble. This is the image from Hubble. We can zoom in. Ah! Look how from the first one to this. So from this one, you see the little two bright, look like star. They look like star. And there's a galaxy in between, okay? So how do we confirm this is a lens system? At that time, 1979, we don't have this picture. This is from Hubble. So at that time, we don't have this picture. How do we confirm this is a lens system? So what they do is they measure the spectrum of these two blobs. And you know what? At that time, around 1979, 1980, this object is very peculiar because by our eye, they look like star. They look like star because it's like a point source. But when you see the spectrum, compared to the real star, it doesn't really match. So, in fact, this object we call quasi-stellar object. Okay, they are not star, but they look like star. And at the time, we don't know what is that. Now we know. Now we understand a little bit better. By the time, we just know this is something close to star, but we don't know what is that. So they observe the spectrum of these two objects. So the spectrum basically is you observe the light coming from this source across all the wavelengths. Okay? So each wavelength basically is like our optical optical waveband. So this is a wavelength band of the optical. So that's basically what you can see, but you can split the light into different wavelengths. And you observe the intensity, that's what you get the spectrum. And they see the spectrum from these two objects. They are basically identical. And that's really, really weird. You have two objects so close to each other, and they are basically, they look the same. So are they really the same, or they are just accidentally close together? So the first time they wrote a paper, 1979, they said, this object, is it a twin quasi-stellar object or a gravitational lens? So this is the first time they got a picture, they got a spectrum, and said, okay, perhaps this is the first lens we discover in human history. And they are right. After we have the more data, you have the higher resolution image like this one, yes, we confirm this is a lens. So this is the first time we found the lens system. But this is really, really small, right? It's really small, it's really hard to see. Now we have a Hubble telescope, space telescope. We can resolve the structures. Okay, so now we are going to watch the movie. I show you how this kind of lensing effect happens. So this is us, we're here, the Earth. This is the source. So the light coming from the source quasar passing through a massive object like a galaxy. And the light will be distorted, even split into multiple images. So that's what you see. This is also a real image. That's how it happens. That's because general relativity, all of this gravitational lensing theory. So you can see the galaxy, massive galaxy at the center. These are coming from the same quasar source, the quasi-stellar object we also call quasar. They're coming from the same source. And you can also see a little bit arc around it. So this arc is also galaxy. Because galaxy is not a point source, right? So it's like an extended source. So when you lens it, it basically distorted like an arc. Okay? So anyone can recognize this hawk? It's a hawk, RCC the hawk. So we are going to lens RCC the hawk. If there's a galaxy pass through RCC the hawk, that's what you will see. So you will see the image is distorted. Yeah, pretty cool. I've spent some time to make this video. Okay, so lensing effect. Lensing system, in fact, there's several types. So I currently show you several. This is one of it, also quite famous. So this is a massive lens system. You can see the arc almost form a ring. So it's called Einstein ring. So to get this, you really need your source and the lens aligned super well. Then you can have this almost perfect circle. So it's super, super, super rare. So to find this system is quite hard. Yeah. And this one's quite famous. We call it the cosmic horseshoe. And there's another one, also pretty famous. So this one you can see there's a lensing galaxy, massive galaxy, and the quasar source split into 4 images. And you can see a very beautiful, almost like a ring. This is coming from the host galaxy of your quasar source. So this is called lens quasar. And your source can also be a supernova. Okay? So this is also a galaxy, and there's a supernova pop up in the galaxy. So this is very, very small. This is like I would say only 0.5 arcsecond, the size, only 0.5 arcsecond. Yeah. Remember the moon is 0.5 degree, so 1 degree is 60 arc minute. And 1 arc minute is 60 arcsecond. Okay, so this only 0.5 arcsecond. This is really, really tiny. And it's really rare because supernova is rare in the universe, okay? And you need to have this lensing effect on top of it. It's basically only 0.01%. It's really rare. It's really hard to find. But we have a few at this moment. Okay? This is another one. If you have a very massive galaxy, it's called galaxy cluster, which means a lot of galaxies all together. Of course, the gravity is stronger. Then you will distort more galaxies behind you. And for this object, I want to highlight this part. It's called cosmic snake. So this is from the galaxy at the early universe, okay? When the galaxy just formed. So basically the lens effect can help us to see the universe further. It's a natural telescope. That's what I put it in my title, a gravity telescope. It can help you to see further. Yeah, because if there's no lensing effect, it's even tinier and it's basically hard to observe. But with lensing, it will magnify the signal. Yeah, and as long as you can reconstruct the structure, then you can understand the early universe structure. They can help us to understand how the universe evolved in our universe. So this one is cosmic snake. This is another one. This is the Urano. There's an arc here. You see this little blob? We suspect this could be a star. Okay, star is really, really small compared to the galaxy, right? So if you want to see the early universe stars, you need this effect. So this is I don't remember the year, but this basically is a star when the universe just formed, and it's there, and you can see it. Yeah. So lensing effect basically help us to study the early universe structure. Okay, another feature I think is quite interesting is lens system can help us to study the whole cosmology. Okay, so how do we do that? I give you a little bit like notations. Later, I will going to show the movie. You will see some notation. This is one is delta t, it's a time difference. Another one, I call it a time delay distance. Basically, it's a distance, okay? But it's coming from some time difference from all of the physics here. Another one is called the Fermat potential difference, okay? And the last one, this is more important, is a Hubble constant. Basically, it's a key parameter to understand the cosmological model. So this is an important parameter to build the whole cosmology. Okay, according to lens effect, this is what we will see, right? We see the massive lenses, and the source will split into multiple lensed images. And here you will see the light will travel from the source, but because the traveling path of these two photons, they are not the same. So the red one will come to us earlier than the blue one. So you see there's a time difference. We call it time delay. And so this is a measurable. We can measure this time delay of the photons coming to us. So I want to sonification a little bit of this effect, so I build this. So you can hear the time difference. Okay, this is real, of course I use a sound, but you can observe the light and measure this kind of the time difference of the system, of the photons. You can derive this Hubble constant. How do you do it? I give you a little bit physics. This is measurable, and this one is all coming from the model. So based on the lensing galaxy mass distribution, we can construct this one. And c is the speed of light. It's a constant. So this is coming from the model. This is the constant. And we can measure this one. From all of this, we can derive this is called a time delay distance. And this distance basically is a combination of your source and the lens and us. Okay, there's some detail. Of course, I show you already a little bit complicated, but in fact, they are really, really complicated. So here I simplified. This one basically the combination of your source and the lens and us. And from this one, you can get this number. So there's a relation between this distance and the Hubble constant. And this constant is really, really important because Hubble constant really determines how the universe will look like. So based on our current result, this is really science result. So the science result up to date, using this lensing effect, we can measure the Hubble constant is around like a 73, 74. Okay? So measure this Hubble constant is important. Lensing just one method. And all this kind of the method is we use something like a geometry, but in the universe. So this method we call cosmography. Okay, use this method, it's called cosmography, we can measure the Hubble constant. But we are not the only one who can measure the Hubble constant. There are also supernova. It's called a distance ladder. So this is another way you can measure the Hubble constant. And the measure is like a 74, closer to the lensing. Another way to measure the Hubble constant is from this cosmic microwave background. So we have the map of CMB. So from this, we can also get the Hubble constant. Here is something quite interesting. Based on the measurement from these three methods, we found that they are not consistent. One is 68, one is 73, 74. This is interesting because this measurement is coming from the Earth, like a local universe. It's an object closer to us. Like a lensing object, it's a galaxy. It's, in fact, it's still quite close to us. Supernova is also close to us. CMB, cosmic microwave background, is the first signal when the light starts to emerge. So this is coming from the very, very early universe. So that tells us the Hubble constant measured from the early universe is not the same as the local universe. This is a tension, and we don't know why it is that. So we're still trying to figure out, is this because our cosmological model is really wrong? Is there any new physics? So this is a really hot topic in our astronomy now. It's a Hubble tension. Okay, so this is a little bit, I know this slide is a little bit heavy, we really can understand. Okay? You have a question?
Yes, the Fermat model
Uh-huh.
and the other one, is that essentially like thinking about it as a path problem? In other words, almost like a ray tracing problem pre-computed by virtue of the distribution of the mass?
The potential part? Are you talking about the potential part?
Yeah, like when you talk about the Fermat model, it just seems to me that in a sense, if you described it as a description of the difference by virtue of the lens model, which is itself a gravity model.
Exactly.
It almost feels like a ray tracing problem.
It's not really ray tracing problem. It's really coming from your lens mass distribution, because based on how the mass in this lensing galaxy, you can really derive this Fermat potential. Yeah. So this is really coming from the theory. Oh, sorry, you have to listen up again. But this Fermat potential, in fact, is also quite tricky because it also depends on how well you can construct your model. And this is also kind of an issue. Yeah, so I agree with you. So far, this is still not perfect. We still try to improve that because I simplify a lot. Yeah. Okay. So I want to. So if you're interested in this topic, I would highly encourage you to look at this video. This is a PBS Space-Time. The host is this guy, Matt O'Dowd. He's my colleague. So that's why you can see we have the same T-shirt. And in this episode, he would describe how astronomers get all of this and why this tension coming from. Yeah. So I highly recommend you to, if you want to know more detail, look at this video. And he has a bunch of the video about the space-time in universe. It's really, really well made. Okay. Now we are going to play again this image. This is an image coming from the ground-based telescope. And the size here is like around 1 arc-minute. Can anyone here try to identify where the lens is? Can you find the lens?
Far right.
Which one?
Far right, sort of towards the center.
Far right.
Right, down, down, down. And
This one?
no, down.
This one?
Yeah.
Oh, okay. I will tell you later. But that's your answer. So you can focus on your potential lens. I show you an image from James Webb. Okay. From here, where is the lens? Huh? This one? This one? This one? Okay, I can tell you. Based on my expertise, there's a lens here. This is a lens. And there's another one is here. You see the arc? Where? This one? This one? Okay. But maybe there are more, but just based on what I know, there are two. One is here, one is here. I just want to show you this one. It's pretty amazing. Because from the ground-based telescope, you basically cannot see. This is a lens system, but from the space telescope, you can see clearly this is a lens. This is a pretty beautiful lens. Yeah. So we have seen several lens systems, something like this. This is like a ring, or you will see the multiple lensed images, like 1, 2, 3, 4, and this is like a 2. And you can also see a huge arc. So the lensing effect we have learned so far is a strong lensing effect. We are going to see a little bit weaker effect. So we are going to learn a little bit weak lensing. So this picture, there's still some strong lensing. You can still see a little bit arc. Okay? But if you kind of close your eye a little bit, you can see the galaxy somehow kind of become a shape like ellipse rotating around the center. Okay? So this is a weak lensing effect. So weak lensing effect is a bit like this. I demonstrate with this figure. Okay, so I don't know if you noticed, there is we call grid illusion. When you try to identify the black dot, it will disappear. So this is called a grid illusion. Okay? But it's not what I'm going to show you. What I'm going to show you is, I'm going to put a lens around like a center, and if I lens it, it will look like this. Okay. So this image was split into multiple lensed images. So this is a strong lensing effect region. Okay. But outside a bit further, you can see the circle. They don't split. They just kind of distorted. So this lensing effect is kind of weaker. But it's still quite useful because if you have a lot of like this kind of signal, you still can reconstruct the lens mass distribution. Okay? So this is what I want to show you, the weak lensing and the strong lensing at the center. Okay. Now, if you look at this picture, what you are looking at here is a bunch of the galaxies, simulated galaxies. There are no lens. Okay, now we are going to add lens slowly. So now we're going to lens it. we put a little bit more massive galaxy in front of this source, and we put more, you will see the image start to distort it. Okay? So based on all of this this signal, how this image distorted, we can reconstruct all the mass distribution in between. So, can reconstruct the mass distribution. So this is the mass distribution based on the shape you measured. And you know what? In our universe, what we can see is only 5%. Yeah. What we understand, only 5%. There are a lot of matter that we don't really know. It's called dark matter. Yeah. It's 30% of the total energy. And basically it's 80% of the total matter in the universe. So 80% of the matter, in fact, is something we don't understand. But we can use this method to reconstruct the matter that we cannot see. So this is called the weak lensing effect, to reconstruct all the dark matter distribution. Why it is important? This is important because dark matter is also one of the main components in our cosmological model. So using this effect, we can construct the matter distribution at a different distance. So you can basically construct the matter distribution from the early universe to now. And why is it important? Because we can compare with the theory. So if you compare with the simulation, so our universe age is 13.8 billion years old. And based on how the component, the recipe you put in your simulation, you will see different structure of the universe. Okay? And from this structure, you compare with the observation. You will know your recipe is right or not. So based on this comparison, we can know how much dark matter component we need to put in, how much like normal matter component we need to put in, how much dark energy component we need to put in. So this is how we really construct the cosmological model. It's one of the methods, so it's quite important. It's called weak lensing. Basically, this technique helps you to reconstruct the structure of the larger universe. Okay, so this is weak lensing. Now we are going to something even smaller. So this is a strong lensing effect. This is a source. If your lens is very, very tiny, like a star, suggested by Einstein, typical lens system, like galaxy scale, is like around few arcseconds. Okay, remember, 1 degree is 60 arc minutes. 1 arc minute is 60 arcseconds. So this typically size is like a few arcseconds. But if your lens is like a star or very small compact object, the lensing effect is basically only micro arcsecond. Micro is 10 to the minus 6, so it's much, much smaller than this one. And remember, this kind of system is already very difficult to detect, right? It's really small. We need a space telescope to see it. This micro arcsecond, don't think about it. It's not possible to observe it. But we can still observe it in different way. This kind of micro lensing effect is so tiny, but it's still lensed. So the light will become brighter when lensing effect happens. So when you see an object, the light change, become brighter, you know there's some lens system passing through it. So I show you a movie. During this movie, I want to demonstrate what micro lensing effect is. So later, this lens star will pass through this source star. And this the curve you see is a time against the brightness. So this observational time, you will see when a lens passes through the source, the brightness will change. The brightness will become brighter because of the lensing effect. Even though you don't see the distinct lensed image, you can still kind of observe this effect. And why this is important? Because this is really, really unique technique to find something very small in the universe. Look at this. This is the source. This is there's a star, lens star, and there's the exoplanet. The planet, not in our solar system. In our sun, it orbits around it, and when it passes through the source, you will observe this light curve like this. So when you see a light curve like this, you know there is an exoplanet. So I want to zoom in to show you. So this little bump is what we are looking for. And why it is important? Because we can find exoplanet. Planet is so small. In other solar systems, it's really hard to find. If we can find more exoplanet, then we have more chance to find aliens, right? Anyone is interested in alien? I am interested in alien, yeah. I want to find alien, yeah. So this is one possible method to find alien, yeah. So to find an exoplanet, microlensing is one method. Another very popular method, just for the education, is called transit. Transit is basically like this. When a planet orbits around the sun, when it's passing through the center, you block the light. So when you see the light have a dip like this, you know there's a planet in another star. So this is also another method to identify or find the exoplanet. Okay. So this is how we progress so far. This is a Kepler telescope. It's a telescope on sky. You observe the sky every day. Try to get this curve I show you. Try to find the exoplanet. So this is a planet. The red dot is a planet he found. Basically, it's from 0.1 of the Earth mass to like 100 Earth mass. So he found an exoplanet here, and our Earth is here. Very soon, next year, we will have another telescope. It's called the Roman telescope. And this is name of the scientist. Her name is Nancy Roman. Basically, he's a scientist who built Hubble. So we also call Nancy Roman, he's the mother of Hubble. So we are going to build a telescope named for her. So it's a Roman telescope. It's also going to observe the sky every day, all the time, to get this kind of light curve. And because the resolution is better, the sensitivity is higher, so Roman would detect more exoplanets in the future. So the potential zone for the light form is roughly around here. So in the future, if we can find more, so the blue dot is not real. We haven't found it yet. We predict we will find a lot of exoplanets in the future that can help us to understand the exoplanet structure. And maybe we can find aliens. Maybe. Okay, that's almost done. So what we have learned today, we learned different type of lensing system. The strong lensing, weak lensing, and micro lensing. So micro lensing, what you can see just a kind of bump in this kind of light curve. So the observable, they are quite different. For the strong lensing, you can see the multiple images. You can see the arc, but the weak lensing, you can only see the ellipticity correlation. And the size also quite different. Even though we call this a strong lensing, but usually the size of the image only a few arc seconds. And the weak lensing, usually the image is huge. Usually around like a few arc minutes to degree. And micro lensing is only micro arc second. It's basically not observable. So the lens mass for the strong lensing, it basically is a galaxy scale. It's like a galaxy. For the weak lensing, usually it's like a cluster, galaxy cluster. It's more massive. So it's like for large scale structure. Micro lensing is smaller. It's like a star. So these are the lens type And also I show you the time scale, micro lensing, because it's coming from a small object. So this light curve usually is spanned around days or months. Okay, so all of this kind of system can help us to study different science. It can help us to study dark matter, early universe, cosmology, large-scale structure, and also we can find some exoplanet, which is very important. Okay, a few takeaways. So gravitational lensing is not only just beautiful, right? It's a nature all magnifying lens. It also can help us to study a lot of science. And this one, general relativity, works very well. We need to use GR to get all the models. So we also learned a little bit history of the lensing. We also saw the first discovered lensed quasar. And we also learned of different type of lens systems. In the future, we are going to find a lot more systems like this. This is really hard to find because imagine if you want to have a lensing effect, you need the source and the lens really aligned very well, which doesn't happen all the time. But in the future, we will have more data, we have a better telescope, so we will have more. And use this subsystem, we can study different science. That can make us very happy. Thank you so much. Yes?
Yes. What has lensing told us about the various different sizes of black holes?
Oh, different sizes. That's very good question. So, okay, whatever. I don't do anything now. Okay, so your question is, how do we study the black holes? That's in fact a very good question. To study the black holes, there are two ways. For the lens system, we have the lens and the source. So it depends on your question. You ask the black hole in the source or in the lens.
Okay. Say in the lens.
In the lens is one way. So usually, let me try to find a figure. How can I do that? A little bit technical issue. It doesn't work. That's fine. Oh, okay. I found it. Okay, let me try to answer your question. For the black hole at the lens, it's possible. So, here, I use this lens as an example. So, all the galaxies, there's a black hole at the center, which is called supermassive black hole because the mass usually around like 1 million to billion solar mass. So, in this galaxy, there's a supermassive black hole. To measure that, it's quite interesting. We need to reconstruct the mass, this lensed feature. Okay? So based on this lens feature, we can, right? It's very bright because of the galaxy. But if we observe this system in a different wavelength, for example, if we observe it in a radial filter, then you don't see this lens galaxy anymore because this light is coming for the optical, like our eyes. But for some component in this source galaxy, we can see it in the radial. So the radial basically can block light of the lens. Okay? Why this is important? So this lens feature, in fact, if there's a black hole or without black hole, there's a lensed image at the center. Okay, you don't see it now because the lensing galaxy block the light. So if we can remove the light coming from the lensing galaxy and check if there is an image at the center, we can kind of measure the black hole at the center of the lens. Because if there's a black hole at the center, it means the density profile is really, really sharp. And then that can give you different lensing effect to kind of remove the central image at the center. So use that, we can measure the black hole at the lensing galaxy. That's one way. Yeah.
So you're looking at the lensing effect of the whole galaxy versus the lensing effect of just the black hole?
No, it's lensing effect still coming from the whole galaxy.
Right, okay.
But there's something very sensitive at the center. Yeah. So the center, usually there's also a very faint image. But if there's a black hole, that can reduce the effect of this central image. So we can use this method to measure the black hole mass of the lensing galaxy. Yeah. Or you just construct the mass distribution of this one based on the profile of your lensing galaxy. Then you can kind of derive what kind of potential black hole mass at the center. That's another way. Yeah. So let's measure the black hole mass for the lensing galaxy. I think more useful, more frequent, scientists try to study the supermassive black hole for the source. So for this case, it's quasar. Quasar is a galaxy, type of galaxy. It's very active, not like our Milky Way. The very active means there are a lot of stars forming in this galaxy. So it's very, very bright. It's not like our Milky Way. So quasar is a galaxy. They are super bright. So when they are at the early universe, far away from us, usually it's like a star. So they can be very bright like a star. And because they are very active, so based on the brightness of this quasar, we can study the supermassive black hole of the source. So that's another way to study the supermassive black hole. Problem? Yes?
I can understand the ring,
Yeah.
because it looks like a star in a regular telescope that's out of focus. I'm having difficulty visualizing how you get multiple images.
Oh, just because the traveling path was split. So if I show you the movie, I show you this one. That will make me a little more difficult to find this. All right. Okay, so I can show you the movie. This one. So because the light will be distorted into multiple paths coming to you. So if you have a weird feeling of this multiple, okay, in fact it's not just in the universe. I have slides. I hope I can find it. Okay, this is a movie I can show you. Okay, I can do this. So, this is happened to our real world. This is a wine glass, okay? It's a wine glass, and this is a dot at the center. So if I run the movie, when the lensing effect happens, you will see become like multiple images. Okay? So when you go to a restaurant, have a wine, you can play with that. So it happens to our daily life. Yeah. So it's optical physics. It's not gravitational lensing, but it's optical lensing. It's exactly the same. The equation is different, but it's exactly the same effect. Yeah.
I have
Yes?
some questions on black holes.
Uh-huh.
About 2 or 3 different questions. First question is, does a black hole bend light or refract it, or both?
The black hole deflect light or bend light, or both? Both.
Both.
Yeah.
Another question, within a black hole, is there the absence of something and the presence of something?
In a
And
black
how-
hole.
Right, and how can lensing reveal something? Does it reveal
Oh,
something within a black hole?
in fact, I think black hole is also like lensing, but the light distortion is much stronger
Within a black hole?
around the black hole. I can show you the movie. Seems like everyone is very interested in black holes. Let me try to. I have a movie of a black hole, so let me try to find it. I can show you. Hmm. Oh, not in this slide. Okay, I don't have here at this moment, but if you come to me later, I can show to you. I can show to you the black hole image, the simulation. But basically, the black hole, because the gravity is so strong, so the light not just bend, it will even rotate around the black hole.
Oh, right.
Yeah, and even suck into the black hole. It never comes out. But the lensing effect,
Is that because of gravitational pull, is that why?
exactly, yeah. So the lensing effect here is a region, the gravity is strong, but not as strong as black holes. The black hole basically is not just bending, it really suck all your light in at the center. Yeah,
Thank you, that was
that was
very
pretty
good
cool.
answer to the question, thanks.
Is the deflection angle given a gravitational arrangement at all dependent on the wavelength? Is there a wavelength
No,
dependency?
it's not wavelength, it really depends on the geometry. It's not really wavelength, independent.
So X-rays will deflect at the same way as a radio
Exactly,
wave.
exactly, yeah. But in X-ray, because the source will be different, will look different, so the lensing image will be different. But how it is stored, it will be the same.
The photon path, no matter.
Exactly,
what wavelength,
it will be
is
the same. Exactly, yeah. Yes?
Is most of the ancient light that Webb is detecting subject to lensing, or is it only a small part?
What do you mean?
The light the ancient light that Webb is detecting,
Yeah.
is most of it subject to lensing or only a small part of it?
Oh, you mean for the James Webb telescope?
Yeah.
Only part of it, because James Webb, they have so many science goals. Yeah. But thanks to James Webb, because we can see deeper.
Yeah.
So when you have more source in behind, you have more chance to have the lensing effect.
Right.
So it's not the main target, because some people want to study the exoplanets, some people want to study the local stars, some people want to just focus on the galaxies, specific galaxies. So not all the image or all the mission is targeted to the lensing effect. Yeah. But some, more, I would say more, compared to Hubble,
That's
is
my
more.
question. The most distant light that it's picking up, is most of it lens?
Exactly,
Yeah.
exactly, yeah. So you have, indeed, thanks to James Webb, we have more lens system now. We find more, many more, yeah. Yes?
You had a video that demonstrated the time evolution of the galaxy, presumably from some time post the Big Bang to about 13.8 billion years.
I think
It
you
essentially looked like a time plot of density of matter in projection into the Earth.
yeah, I know which one you're talking about. I need
So my
to.
question in that system, in that modeling system,
Huh?
is are the dominant forces in that model purely driven as a function of gravity?
No, it depends on the, because large scale structure. So is not just pure gravity. Because gravity only coming from matter. So for that kind of the study, you also need to put the component of, like, for example, the dark energy, which is 70% of the energy in the universe. So that you can see how the universe expand, and then you can compare with the simulation.
So the notion is, if the model is parametric in terms of what we're postulating as potential dark energy force or a dark matter concentration, then the sort of time traversal and final position of the elements in the model should in theory be comparable.
Exactly, that's correct. Exactly. Yeah. So you're also right. Depends on the component you put in your model. Will also give you different shape of the galaxies, and you can also compare that with the observation.
You mentioned dark matter, 70% of the energy, and yet I thought there was no way of measuring any mass of dark matter, therefore how can it be energy? I'm just confused. Dark matter, I thought they know it's there only because there's a void, but they don't even know what dark matter is. Am I wrong?
Your question is dark matter is wrong, or?
Is dark matter actually, you said it's energy, and energy is supposed to equal mass. Is that
No, dark energy is dark energy. Dark matter is dark matter. They are not the same. So,
Oh, yeah, okay. Two different things.
yeah, it's totally different like energy component in the universe. So dark matter is, we know something need to be there, and there's a matter. But this matter, we cannot explain by our standard model, the standard particle model, that we can find what is a particle can really connect to dark matter. This we don't know. Yeah, but we know there's a mass. But dark energy is even more intriguing. We don't even know what is that. It's not even mass. It just can help the universe to expand. And we need that to compare with the current data. Yeah, that's the dark energy. Basically, dark energy, you can imagine, is like a negative pressure to push the space-time away. So this is dark energy. And dark matter is matter. It's a gravity. You will still pull stuff together. Yeah. Yeah. Just gravity.
This is the effect of dark matter.
Exactly. Yeah. So that's why lensing is so useful, because dark matter is you cannot see, but this effect, we know there's a matter, so we can construct the matter that you can observe. Okay?
Good. Okay.
Thank you so much.
Thank you so much. Thank you all for being here tonight. We'll reconvene in the fall with our next series of lectures for all of you. Thank you all for being here. Safe home.
Hope you enjoy it.